Hi guys, I'm Dinesh.
And this is Kiran, and we are part of Stanford Network Systems Group in Electrical Engineering Department at Stanford University. In this video, we are going to demonstrate a fully functional full duplex radio that can adapt to changing environmental conditions. The architecture of our full duplex radio is based on the paper Full Duplex Radio by Varadia et al. We will demonstrate the working of a full duplex radio by simultaneously transmitting and receiving OFDM packets that are used by existing 802.11n half-duplex Wi-Fi radios. We have implemented the full duplex radio using programmable radio platform WARP in combination with custom cancellation hardware. We will first describe different units of our prototype full duplex radio and then demonstrate the operation of this radio. Full duplex radio requires cancellation units to cancel the effect of self-interference caused by the leakage of transmitted signal on the receiver chain. The cancellation unit for our full duplex radio has two major parts. The first part is a cancellation filter that works in RF domain. We will also occasionally refer to this filter as analog cancellation. This filter is implemented with a bank of fixed RF delay lines and digitally tunable attenuators. The single antenna that both transmits and receives signal is connected to the full duplex radio via the circulator. The input of the circulator is connected to the transmit chain's power amplifier that can transmit OFDM packets with signal power up to 20 dBm. The other output of the circulator is connected to the cancellation circuit, where the output of the RF cancellation filter is combined with the received signal. The received signal consists of multiple delayed and scaled copies of the transmitted signals, leaking through several parasitic paths along with the received signal that the radio wants to decode. The output of the cancellation filter tries to create inverse of the copies of the transmitted signals that have leaked to the receiver side. After combining the received signal and the cancellation signal, the resulting signal, which consists of the received signal and some traces of the transmitted signal, is fed into the receiver chain located in the warp node. Here, the signal passes through the traditional receiver chain architecture consisting of LNA, mixtures, and ADC blocks. The warp node transfers the digital IQ samples of the received signal after analog cancellation to a PC via Ethernet connection. The PC runs MATLAB, where most of the processing algorithms are implemented. We process the digital samples generated by the ADC to remove the remaining traces of transmitted signal by means of digital nonlinear filters. We will also occasionally refer to this filter as digital cancellation. The parameters of the digital nonlinear filters as well as the attenuator values of the RF cancellation filter is continuously adapted to account for any changes in the environmental condition. These changes may be caused, for example, by moving reflectors in the vicinity of the full duplex radio. We have implemented the logic for adapting both the analog and digital cancellation filters in MATLAB. We have also implemented baseband processing units that decodes the receiving OFDM packets in MATLAB. This baseband decoder in fact complies with the baseband processor used for 802.11n half-duplex Wi-Fi receivers. We will now demonstrate the working of a full duplex radio by creating radio links using this prototype full duplex radio.
We'll be showing you a point-to-point full duplex radio link.
We can see on the left hand side, we see the signals after different stages of cancellation. The first signal, blue, is the transmitted signal. The second is the red, post analog cancellation signal, and the black one is post digital cancellation, and the green is the noise floor. As we can see, the black is very close to the green, which means that we have cancelled entire self interference to the noise floor. Now, as you can see in the middle, we have the setup itself, and we bring a metal very close to the setup, and we can see on the right that the taps, analog cancellation taps, quickly updates themselves to recur from this environment, and thus when we remove this metal out, this taps recover back to the original position. Also, the digital taps are continuously adapted because there is always some movement in the far field motion. It keeps adapting to that environment. So the last part showed us the cancellation. In this part, we look how does the link performs. So we continuously are receiving a signal from a radio 2 and we look at the radio 1, and the left hand side plots the different signals at radio 1, the transmit signal, the blue as usual, the red signal post analog cancellation, and the black signal post digital cancellation is essentially showing the external signal which we are receiving from radio 2, and the green signal is the signal in the half duplex mode when you are not transmitting anything. As we can see, the blue and the green signal are almost similar, which makes sense that cancellation is working. To verify further, we look at the IQ demodulated plots on the second column. As we can see, without full duplex, we can't able to make out the 16 QAM. With full duplex cancellation, we can make out the 16 QAM as in the black plot very clearly, and green is the half duplex. As we can see, the green and blue have similar tightness or the spreading of the QAM signal, which shows the link isn't impacted very much.